Alright, so we're going to be talking about section 4.4. And 4.4 is just kind of putting everything we've learned together into just how to sketch a curve, so curve sketching. And so here's the guidelines the book gives. It's you're going to find the domain, you're going to look for your intercepts, you're going to look for symmetry. So not too much difference from before. So principles of symmetry, they exist. Like if the function even or odd, you only have to look you only have to look for the positive values, and then negative values you can just figure it out. If it's periodic, which we'll show, you only have to graph it figure out stuff for a small section, then just repeat it over and over again. We're going to learn stuff we learned in like 1.6, how to deal with asymptotes, and figure out, if it's going up and down. We're going to find intervals of increasing and decreasing. We're going to find local max and min values. We're going to look for concavity, points of inflection, and we're going to sketch the curve. So all of this is very, very, very much like we did in the last section, just we're going to kind of put it all together for the next following problem. So let's dive into it. Let's just get into one of them. So let's look at this. So we're going to look here at here. And so where's the domain? Well, the domain, I was kind of doing the order that the book's doing it. So in the domain, so domain is everywhere except for where x is equal to 1 or negative 1, because here if that's true, this ends up being 0. So here we're going to say the bottom part can't be 0, so x squared minus 1 cannot equal 0. That means x cannot equal 1, negative 1 or 1. And so here we're going to say our domain is from minus infinity to negative 1, from negative 1 to 1. Put little unions in here, from 1 to infinity. Okay, and so here we're actually going to have these little asymptotic lines that exist at both negative 1 and 1. And so let's go ahead and draw those in. And just for the sake of this one, I'm going to have each tick mark mean 2. So here we'll end at 5. And then here we'll do each tick mark is 2. We'll end at 5. And same over here. So here would be 2 and 2. And so let's do that. Alright, let's look for the x and y intercepts. Alright, so the x-intercept and the y-intercept in this case are the same, so we're going to look for intercepts. And the intercepts, we're just going to set this equal to 0 and find out where that's true. And so we have 0. Where's this equal to 0? So f of x equals 0 when x is 0. As we can just see right here. So we have 0, 0. And the same thing true if we plug in 0, f of 0 is 0. So this is our only intercept we care about. So our only intercept is right here at this point. We know we have two lines not in the domain, and these become asymptotic lines, and so we're going to deal with those right now. Let's go ahead and draw those in. So that's at negative 1 and 1. All right. We also have another asymptote. Let's go ahead and deal with the asymptotes right now, as long as I'm talking about them. Asymptote. So we have the two where the function doesn't exist. Let's also look at a horizontal one. So let's look at the limit. Before I do that, let's just talk about a symmetry real quick. So symmetry. So this ends up being an even function. AKA, if I plug in f of negative x, I'm going to get f of x out. And that's because here, this will square it, and this will square it. And so if I put in positive or negative values, I'm just going to get back the same. And so technically, once I know this is true, I only have to look at the positive half of the function. Because whatever I draw here, I'm just going to mimic on this side, right? And so this will look, and so no matter what it is. So I really need to look at the positive half, and that's going to make it a lot easier. Because here, if we look at the asymptote, I'm just going to have to send x to positive infinity. And the same thing will happen for negative infinity. So we're just going to look at positive infinity. And if I do that, x squared over x minus 1. Notice if I get infinity over infinity, you can take the derivatives, you can do it 1,000 different ways, and you're going to come out that here, or you can just divide out like we used to. So we're going to divide out by the highest power here, so we 1 minus 1 over x, or x squared. So this will go to 0. So this just goes to 2. And so that's our horizontal asymptote. So here we had two vertical asymptotes at the horizontal asymptote occurs at 2. So we'll go ahead and draw that in. So I'm going to write horizontal asymptote occurs at y equals 2. Okay. So here we have our asymptotic lines. And so here we can almost start to see how this thing's going to come together. All right, so let's look. So what have we done? We've done domain, we've done intercepts, we've done symmetry, we've done this. So let's find intervals decreasing and increasing. All right. And so let's just do increasing, decreasing. Increase or decreasing. And so in order to do that, we need to find f prime of x. And if we do that, we're just going to take, this becomes 4x times x minus 1 minus 2x squared times the derivative of this. So this is my f and my g. So it's f prime g times f g prime and minus f g prime, which is this, all over g squared. So this would be x squared minus 1 squared. We simplify that. We're going to get minus 4x over x squared minus 1 squared. And so what do we have here? So we have, where does this equal 0 or does not exist? Well, this equals 0 at x equals 0, and it does not exist where x is equal to 1 or negative 1, right? So 0, 1, or negative 1. Notice here we only need to look at really at 1. So here, I'm going to only do half the intervals. And the reason I'm going to do half the intervals is because I have the symmetry. It's even. And that's why we find it. So from 0 to 1, I just need to know what's the sign value on f. And then from 1 to infinity. Well, from 0 to 1, the sign value on f prime, so if I plug in like 0.5, this is negative. This is positive. And so we have it to be negative. So this is negative, and this is negative, and this is negative, so this is also negative. And so here I have it decreasing and decreasing. So it's decreasing and decreasing. We're going to look at concavity. So let's look at concavity here. All right, so we're going to have to find f concavity. We're going to look at f double prime of x. And if you crunch through this, it ends up being 12x squared plus 4 divided by x squared minus 1 to the 3rd power. So, where does this? It doesn't exist at 1. And x squared plus 4 is always positive, right? And so this can't equal to 0, so we look at 1. So here we have x is equal to 1 and negative 1 or 1 are points, the possible points of inflection. So again, we're going to look from 0 to 1. We're going to look at f double prime. And we're going to go from 1 to infinity. F double prime here, since this is always positive, and from 0 to 1 this is negative. This will be negative, so I'm concave down. So here I'm down, and then this will be positive, and this will be positive. So I'm up in this case. And there we have enough. We should have enough to do everything. So let's go ahead and graph this. The only thing I'm missing here that might be useful if I had from negative here at 1, it's kind of inconclusive, but let me show you what happens here. All right, so I have a point here. So let's just start graphing it. I have enough information to graph this perfectly now. So let's look at what I have here. I know it's decreasing and decreasing, right? I think I'm missing one last thing real quick. And that is, how does this function behave around the asymptote? And so here I want to find the limit as x goes to 1 positive and the limit as x goes to 1 negative. And I'd have to do the same for -1 and or for negative and negative, but since for even, we only need to focus on the positive half, and I'll show you why in a second. All right, so here if I go from 1 negative, so from this side, that means I'm going to have 2x squared over x squared minus 1. That means this is going to be ever so slightly less than 1. And so this becomes negative. This will be positive, so this goes to minus infinity. Here at positive 1, this on the bottom is going to be slightly over 1, and so this will be positive. This will be positive, so it goes to positive infinity. And so we have everything we need. So let's do this. So we're going to start here at our point, and we know that it's concave down, and it's going to negative infinity. So it looks like this. And once I've drawn this part, I've actually, since it's even, I just mirror that over here. And here we have our one local max, right here. Then from here, I'm going to start from positive infinity, because that's where it starts over on this side. And I'm concave up at this point, so I'm going to be, so concave up looks like this, concave down looks like that. I'll be decreasing, and I'm going to be going towards my asymptote, and so it comes in, goes like that. And since this is an even function, we just mirror it on the other side. And here we have completely sketched everything. We know the concavity at all points. We have our local maximum. And everything goes to there. And so this is just a way of trying to put everything together in order to produce a picture. So let's do this again. Let's do it for a different one. So let's do something a little bit more different. So here, let's look at the domain. And so what are we going to try to do here? So we're going to do domain, intercepts, and symmetry. So let's start with the domain. So the domain of this is all real numbers, right? There's nothing here can go bad, right? Either the x can take all real numbers, x can take all real numbers, the multiplication can take all real numbers. So this is all real numbers. So the reals are all reals. Or if you want to put it in interval notation from negative infinity to infinity, all this is the same. All right, the intercepts. The intercepts. So here we're going to look for so f of 0 will give us our vertical intercept. F of 0 equals 0. So that's one of our intercepts. And then we're going to find where the function's equal to 0, and that will give our horizontal intercepts. So e to the x, notice that this can't be 0, so this must be 0, so the only solution here again is 0, 0. So that gives us both our intercepts. So we're here, you plug in f of 0 to find your vertical intercepts, and you set it equal to 0, and that'll give you your horizontal intercepts. Alright, symmetry, this doesn't have any symmetry. So the symmetry here is none. So it doesn't help us out. So we're going to have to kind of crunch through the entire thing, which is fine. Let's kind of look at the asymptotes. So there, oops, one more. Let's look at the asymptotic behavior. And so we're just going to look at what happens when asymptotes. Let me see if I can spell that better. A-S-Y-M-P-O, the asymptotic behavior. And so here we're just going to look at the limit as x approaches infinity of x e to the x, and then we're going to take the limit as x approaches minus infinity of x e to the x, or minus e to the x. So let's look what happens here. Well, as this goes to infinity, this goes to infinity, this goes to infinity, so we safely say this goes to infinity. This goes to negative infinity, this goes to negative infinity, this goes to 0, and so we have infinity times 0, so what must we do? We're going to have to rewrite this in for the L'Hopital's rule, so we'll write this as x over e to the minus x. And so this will go to infinity over infinity. Oops, I forgot to write something. This is the limit as x goes to minus infinity of x over e to the minus x. This gives us infinity over infinity, so we can apply L'Hopital's rule and take a derivative. And so this will give us 1 over negative e to the minus x, which is just equal to, and so if I plug in 1 over e to the minus x, that's the same as e to the x, or minus e to the x. If I plug in negative infinity here, I just get 0. So we know our behavior on this side, it'll go up to infinity, and over on the left it should go to 0. Alright, so let's find intervals of increasing and decreasing. So let's look at our intervals of increasing, decreasing. Alright, so we find f prime of x. So f prime of x is equal to x e to the x plus 1 e to the x, or in other words, x plus 1 e to the x. And so where is this 0? So we set this equal to 0. So 0 equals x plus 1 e to the x. X can never be equal to e to the x, so this is 0 when x is equal to minus 1. Alright, so let's look at our little chart. So we're going to go from minus infinity to negative 1, and then from negative 1 to infinity. We're going to look at the sign on f, and here we plug in, say negative 2, this will be negative, this will be positive, since this is always positive. This is negative, and then if I plug in like positive 2, this is positive, this is positive, so this is positive, so it is decreasing up until 1, and then increasing from then onward. Alright, and notice here we have a local min, because I go from decreasing to increasing. So that local min occurs right here at negative 1. Let's look at our concavity. Alright, so we're going to take the second derivative here of x, and so that would be, we'll crunch through it. So it equals x plus 1 e to the x plus e to the x, so this is equal to x plus 2 e to the x. We'll set that equal to 0 and solve. And when we do that, we see that e to the x cannot be 0, so it must be this, and so that means x is equal to minus 2. Do the same thing here. We're going to go from negative infinity to minus 2, and then from minus 2 to infinity. We're going to look at the sign on this. So if I plug in negative 3, this is negative. If I plug in positive 3, this is positive. So this is concave down. This is concave up. And notice here we have a point of inflection at minus 2. So we have everything to get us started. So let's get drawing. So here, and once again, I'm going to use two hash marks, mean 1 dot. So this will be at 5, this will be at minus 5. And we'll use the same up here to draw it in. All right. So let's look at this. So here we have a point here. I know at -1, I'm at a local min. So somewhere here would be a local min. And then here, here I have some point of inflection. And so here, it is concave up, and it's going towards 0. It's decreasing, it comes down. Here I'll hit my local min, and then here this goes from concave up to concave down, and then, or from concave down to concave up right here at this point. Here we have our local min, and then it comes up and goes to infinity. Okay. All right, so I have not checked either of these yet, so let's do that real quick in Desmos. Open up Desmos. All right, I'm just going to hit our graphing calculator. So let's just graph x e to the x. And look, our little picture here looks very, very much like the picture we have there. It comes in, at -infinity comes down. Here we have concave down, then it goes to concave up. Here's our minimum. It goes to the origin and then goes up to infinity. All right, we'll go ahead and graph the other one because I didn't do that yet. Let's just double check that real quick. That was 2x squared divided by, x squared minus 1. Okay, and notice how that looks very much like we predicted it looked like. All right, so let's do the last one. The last one, we'll just go ahead and click on it. And just for a change of pace, when we do this last one, I'm going to show you the answer and then we'll work towards it. All right, so here, what do we have here? We have cosine x on top, so cosine x on top, and then what we have on bottom is 2 plus sine of x. So we have this weird looking thing, right? And so we'll go ahead and produce this for us. All right, so let's start with finding everything we want to find. All right, so the first thing we want to find is our domain. Since sine can take in everything, cosine can take in everything, and since sine is only between -1 and 1, this will never be to 0. We have it to be all reals. So the real numbers. And this is a sign for all reals. All right, we want to find our intercepts. Intercepts. So when f of 0, when f is equal to 0, we plug that in, we get 1 over 2 plus 0, so this is a half. So we have a thing of 0 and a half. If we want to find, when 0 equals cosine f, this will give plus 2 sine of x. All we really need here is cosine to be 0. And so cosine is 0 at pi over 2. And so here we have pi over 2 plus plus pi and pi, so at every pi and pi this is 0. All right, since we have an even function on top and an odd function down below, this becomes neither even or odd. It just doesn't work out that way. And so for symmetry we don't have anything. It's not just for symmetry we won't have any, it won't be even or odd, but it is periodic, right? So it's not even or odd, but it is periodic. Very odd. See if I can spell that word. Periodic. So it is periodic. In fact, because here I have sine on top and cosine, and that's the only x and y, x plus 2 pi is just going to equal to f of x. So we only need to find stuff in a very small window between 0 and 2 pi. So we only need to consider stuff between 0, x between 0 and 2 pi. If we find everything here, we'll find everything. Okay? For the asymptotic behavior, this has none because this is the asymptotic behavior. If we try to figure, if we send it to infinity, since this oscillates and this oscillates, we have the same problem we had before, right? With the limit of sending these two, so this doesn't have any asymptotic behavior. And so sometimes when you go through our little list here, that we have way up here, you know, some of these just doesn't help us. Like there is no asymptotic behavior, or there wasn't symmetry one time, or there'll be an intercept because it should go through y, but they may not be, right? I can think of curves that don't go through it, you know, but domain's important. So let's just move on to our intervals. All right, so we want to find out where this is increasing or decreasing. So let's do asymptotes. There is none. So let's just go to increasing, decreasing. So here we want to find f prime of x. And since this video is getting a little bit long, I'll just go ahead and cut to the chase so you know how to take a derivative of sine of x plus 1 over 2 plus sine of x squared. And we set this equal to 0. So if we set this equal to 0, and so this will be 0 and the top part is 0, so we just only have to look up there. So we just said this is 2 sine of x plus 1. That means where is sine equal to minus sine of x equal to minus a half? Well, that's at 7 pi over 6 and 11 pi over, 11 pi over 6. Oops, let me make that over here. Equals half, that means x is equal, since I'm only looking from 0 to 2 pi, that'd be 7 pi over 6 and 11 pi over 6. And so we're just going to go from 0 to 7 pi over 6, and then from 7 pi over 6 to 11 pi over 6, and then from 11 pi over 6 to 2 pi. And notice that since we have periodic behavior, we only need to look in here, so let's just look at the sign on f prime. And so here, this will be decreasing, since here this will be, here we'll have positive sign, and then this is, the bottom is always positive, so this will be positive sign, so this is decreasing, this is also decreasing, and then it finally becomes increasing for this point. So if you just look at the signs, you'll get this. Hold on. So it's decreasing from here to here. From here to here, it'll be increasing. And then from here to here, it goes back to decreasing. Sorry. Be very clear about this. How do we do this? We just test a point. So that's an easy point to test here. We'll just test pi over 2. Well, pi over 2, this just becomes positive. And if the top part is positive, overall will be negative. Here, we can just test pi. Oh no, pi's not far enough. We can test pi over 3. This becomes -1. So -1 times -2, so this overall is negative, so we get a positive. And then here we can just test the point of 2 pi, and we see that this is, again, negative. And so here it's decreasing, increasing, decreasing. All right, the last thing we need to check right now. So what do we have here? We have a local max. So here we have what goes from decreasing to increasing. That's a local min. So we have a local min here. And then we have a local max here at 11 pi over 6. So 7 pi over 6 is a local min. 11 pi over 6 will be our local max. Let's look at concavity. And then we should be able to go. Alright, so concavity here. So we're going to take the second derivative of x. And so we'll have this be minus 2 cosine, minus 2. And then make this, back up for 1 second, make this very clear. Minus 2 cosine of x, 1 minus sine of x, all over 2 plus sine of x cubed. All right. So here we want to test points. Notice that this will always be positive. Since sine can only go from -1 to 1, this is always positive, so we don't worry about that. The other thing we need to worry about here is when this top part is 0. So when is this 0? Between 0 and 2 pi. Well, we have it at so cosine would be, so let's look for when this is 0. So when this top part is 0. Notice this bottom part is always positive. So when this top part is 0, it's due at cosine x, 1 minus sine of x. All right. So what points do we have here? We want to know when. So here, we can get rid of the 2. And so cosine of x is at pi. And then here we have when is this equal, so there'll be, so here the points we need to look at here are pi. Let me be very clear on this. So here we go to this. So when cosine is 0 at, whoops. Let's be very clear. Cosine of 0 is at 0 at pi over 2. Hold on. See if I can remember my trick. And 3 pi over 2. Sine of x will equal to 1 where? Well, sine of x equals 1 at pi over 2. And so these are the only 2 points we need to test. Okay, so let's go ahead and put that in. So we're going to go from 0 to pi over 2. And we're going to go from pi over 2 to 3 pi over 2. And then we're going to go from 3 pi over 2 to 2 pi. And so we're going to look at f double prime. Sorry, it's getting a little bit cramped. So let's plug in a value here. Let's plug in, I don't know, pi over 4. If I plug in pi over 4, we're going to see that this is positive. So this will always be positive, and so with this negative sign here, we'll have to go back to this. This is always positive. So this is positive. This is positive. And so this will overall be negative. Since positive, positive, and this negative, and this becomes negative. From here, if I plug in values from pi over 2 to pi, this will be cosine. Here it turns negative, so this is negative, and this will remain positive, so this is So positive, negative, positive over positive is still positive. And then here, if I test this point, I'll find a negative. So this is concave down, up, and then down again. Okay, and so our point of inflections are, so here at pi over 2 we have point of inflection. So here's an inflection point and here's an inflection point. Alright, so let's go put this in. We have everything all built. Let's go put it in. So where is our intercept? Our one intercept here is 0.5. So I'm going to, let's see how I want to draw this. Let's make this 1 and let's make this 2. Let's make this -1 and this -2. And here, I'm going to put in units of pi, just because I'll make our lives easier. 2 pi, and then we'll have 3 pi. And then we'll do the same thing over here for minus pi. So minus 2 pi and minus 3 pi. That'll look a little bit more like a pi. All right. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4. That didn't look symmetric. Let's make it symmetric. There we go. All right, so our first point here is about halfway up. I have this, and we only need to graph from here to here. So what do I know? What do I know? How am I going to fill this out? Here, I know I'm decreasing. So at pi over 2, so halfway through, I know I'm going to hit this point. I'm going to go through a 0 right here at pi over 2. I know I'm going to go through that point because that's here on our, so here we have this and this, and these are the only two. Oh, and 3 pi over 2, which would be here. So I know I'm going to go through these 3 points. So here, put in my intercepts, and I know what I'm doing. So let's go through. There is no asymptotic behavior. So I'm going to start decreasing until I'm at 7 pi over 6, and then I'm going to start increasing. And I'm going to start at concave down. And then at pi over 2, so actually at this point, I'm going to switch back to concave up. So this is going to start concave down. It's going to flip over to concave up until I'm a little bit past pi over 2. And then it's going to go from, I'm still going to be concave up, and I'm going to go from decreasing to increasing. So I'm going to go up. And then it's going to come up. And then here, at 3 pi over 2, I'm going to switch from concave down to concave back up until I hit 11 pi over 6, which is really, really close to pi over 2. And then I'm going to go, and I'm going to turn around and come back down. So here I've drawn this concave down, and then concave up to concave back down. Here are my inflection points. Here I'm going down, then I'm coming back up according to my min-max point. So this is my min, this is my max. And this min point occurs at 7 pi over 6, so just a little bit past pi. This occurs at 11 pi over 6, so a little bit before 2 pi. And then I just repeat. And I just repeat, and that's going to come down a little bit past and go up, and then this is going to come back. And then here I'll just draw it backwards, so this is going to come up a little bit, and then go down, and then come back up, and onward, right? Now, let's double check again with our happy graph. Here's our happy graph. So here comes in, here at pi over 2, it goes through 0. Here I hit my maximum at pi over 6, and it's at -half basically. Comes back up at 3 pi over 2, we hit 0, and then here at 11 pi over 6, we hit a max. A new max at 5.77, and then it starts heading back down and repeats. Okay, and so that's how you do that. So let's review really quick what we did, and we'll call it good. Here, what do we do? Oops. If found the domain of all real numbers. We found the intercepts. The intercepts at 0 and pi. So our horizontal intercept is here. And our vertical intercept occurs at pi over 2 plus n pi. So pi over 2 plus n pi would be 3 pi over 2 plus n pi, or minus n pi would be minus pi over 2 plus minus 3 pi over 2. So those are always zeros. This is a periodic function since I have sine and cosine, so it's every 0 from 0 to 2 pi. That makes our lives easier because we only have to find answers between 0 and 2 pi. There are no asymptotic behaviors because this and infinity goes this, and this actually never can be 0, so we're safe. Where's it increasing and decreasing? We take a derivative. We set that derivative equal to 0, and that's where just the top part equals to 0. We solve for our sine function, right, and we get 7 pi over 6 and 11 pi over 6. Within our domain, we're going to go from 0 to our first critical point, and then to our next critical, and then from that critical point to the next one, and then from that one to the end of our domain. If it switches from decreasing to increasing, that's a minimum. If it goes from increasing to decreasing, that's a maximum. And we look for these signs, and we do this by just plugging in a number. Here, we just chose like pi over 2, and we can plug that in and figure out where this, if this was positive or negative. And go ahead and use a calculator. Just go ahead and use a calculator this. I'm trying to do it in my head, and that's why I kind of pause for a second. Then we check concavity. So we take the second derivative and we calculate that. And this takes a second to calculate. And so do that. I already pre-calculated it for the video. Here we're going to find out where this is 0. Well, this is 0 where the top part's equal to, where the top part's equal to 0. So we set that up. So where's cosine of x equal to 0? Well, that's a pi over 2 and 3 pi over 2. And then where does sine of x equal to 1? Well, sine of x equals to 1 at pi over 2. And so here we have our two solutions. We're going to check from this to the first point and then onward, just the same thing we did here. And it goes from up and down, and if we switch from up to down or down to up, these are points of inflection. And then we just take all that information and graph it. And that's the end of this video.